Fluids in motion. There's two types of fluids in motion: steady flow or streamline or laminar flow, and the other one is turbulent flow. Laminar flow. Laminar flow is the particles in the fluid follow streamlines, and the motion of particles in the fluid is predictable. Fluid follows smooth path, which is do not cross over one another. This is how laminar flow looks like. Next, turbulent flow. The fluid is characterized by erratic, small whirlpool and circle. Turbulence happens when two fluids with different density are flowing past each other. For example, cigarette smoke. This is how turbulent flow looks like. Continuity equation. The mass flow rate has the same value at every position along a tube that has a single entry and single exit point for fluid flow. Continuity equation. This is the picture that I got from internet. Flow rate through A1 is equal to flow rate through A2. So we can see that rho 1, A1 and V1 is equal to rho 2, A2 and V2, which is same as mass flow rate at position 2 is equal to mass over T equal to rho 2, A2, V2. Meanwhile, mass flow rate at position 1 is mass over T equal to rho 1, A1, V1.
Next is Bernoulli's equation. But firstly, what is Bernoulli's principle? Bernoulli's principle states that as the speed of a moving fluid increases, the pressure within the fluid decreases. Where the velocity of a fluid is high, the pressure is low, and where the velocity is low, the pressure is high. This is the Bernoulli's equation. The equation states that the sum of these three terms remains constant along a streamline, where P is pressure exerted by the fluid, V is the velocity of the fluid, rho is the density, H is elevation, and G is gravitational acceleration. Bernoulli's equation can be considered to be a statement of the conservation of energy. It says that along a streamline, the sum of the pressure energy, kinetic energy, and potential energy remains constant. The example that we apply in Bernoulli's equation is to flow through a pipe which has change in diameter. We use the Bernoulli's equation to see how the pressure changes as the flow passes from the larger to the smaller diameter. Bernoulli's equation is usually used to compare the flow at two different locations. As we know, the velocity at the small area is higher than the velocity at the larger area. So the pressure at the small area that has high velocity is the pressure is low, and the pressure at the larger area is high because velocity in the larger area is low. So Bernoulli's equation is usually used to compare the flow at two different locations. So it can rewrite back with energy per unit volume before equal to energy per unit volume after being on the streamline. This is example of the application of Bernoulli's principle that we do on our daily life, which is how the plane generates lift. The fluid flowing above the airfoils travel faster than fluid flowing below it. This creates an area of low pressure above the airfoil and area of high pressure below it, and this causes to generate lift. And then the drinking water tank with tap. Bernoulli's equation explains how to calculate the water drain when we open the tap. Firstly, define 2 points along the streamline and apply Bernoulli's equation. So this is the simple example of experiment to understand the Bernoulli's equation, which is the first one is when we blow between the two balloons, They will be collapsed or attached to each other because when we blow, the velocity is high and the pressure is low in between the balloon. So the pressure in other side of balloon will push them. And the second one is when we blow above the paper will go up because the pressure below the paper is higher than the pressure above the paper due to the high velocity.
Okay, so here's what...
Viscosity. Viscosity is the resistance of a fluid to a change in shape or movement of neighboring portions relative to one another. Viscosity denotes opposition to flow. The reciprocal of the viscosity is called the fluidity, a measure of the ease of flow. Viscosity may be thought as internal friction between the molecules. Such friction opposes the development of velocity differences within a fluid. Fluid with higher viscosity will have more friction between its particles. Next, let's look into the application of viscosity. There are a variety of applications of viscosity, and this is the three that I found. First one, drug companies manufacture medicines such as cough syrup that have a high viscosity yet are still drinkable in order to cool and soothe the throat. Next, second one is the highly viscous liquid is used to damp the motion of some instruments, and it is used as a brake oil in hydraulic brakes. Then number third is maple syrup industry depends on controlling the viscosity of a fluid. Maple syrup comes from the sap of sugar maple trees. The sap itself is thin, runny, and not sweet to the taste. However, when the sap is heated and most of the water has evaporated, the result is thick, sweet, and flavorful syrup. Application of viscosity in medical. Viscosity is also an important consideration in medical practice, as humans have many different fluids inside them. For example, blood is more viscous than water. When it leaves the human body, it begins to rapidly clot in a process called coagulation, increasing viscosity even more. This is usually very helpful as it forms a barrier to prevent more blood from leaving around, but blood continues to clot even when outside of the body. This means that even donating the blood, the clot increases the viscosity to such point that it will be impossible to use the blood after a certain point. It will not be able to flow into or out of the body back very well at all, and it will actively harm someone if it given to them. To solve this, anticoagulants such as citrate are added to blood bags to ensure the viscosity does not increase too much. This allows the blood to flow easily out of the bag into a recipient body.
So, in this part, I want to explain to you about Poisson law. So, the meaning of the Poisson law is a pressure drop between two ends of a pipe is generated due to fluid viscosity. The pressure drop is inversely proportional to the fourth power of the pipe radius r. So, what is the importance of Poisson law actually? So, the Poisson law equation is useful in determining the vascular resistance and hence flow rate of intravenous fluid that may achieve using various sizes of peripheral and central cannulas. So in this slide, you could see the equation of the Poisson law. So basically, in this equation, this law shows that the volumetric flow rate of the viscous fluid through an enclosed pipe is proportional to the fourth power of the pipe dimension in the cross-section. If one likes, this could also be written in terms of the second power of the cross-sectional area. The point here is that the flow rate is very sensitive to the change in the cross-sectional area of the pipe. Small changes in the pipe radius are amplified with the fourth power impedance, producing a very large change in volumetric flow rate, assuming all other parameters stay the same. So lastly is the application in the Poisson law. Poisson law is a simple relationship between the laminar flow rate in the capillary tube and the material or system parameter, namely the tube geometry, material dynamic viscosity, and the pressure gradient in the system. In fact, The relationship between these parameters is simple enough to be derived from a forced equilibrium equation. The use of Foy's law is normally discussed in terms of hemodynamics, as it explains the effect of blood vessel constriction. However, it applies generally to any area of fluidity. Perhaps the most popular application area where Poisson law is considered is hemodynamics. Because the volumetric flow rate is so sensitive to changes in cross-sectional area, Poisson law is used to explain why constricted capillary lead to higher blood pressure. A slight vein constriction would reduce the blood pressure rate, however, the heart compensation would working harder to increase the blood pressure and keep the blood flow constant. This explains why vein constriction and high blood pressure are related.